All right, let's dive into this. When we picture the cities of the future, our minds usually go straight to massive skyscrapers, fleets of autonomous vehicles, maybe some sleek futuristic architecture. But the real magic, the actual heartbeat of a smart city, it's entirely invisible. Today, we're focusing this explainer on that invisible infrastructure. We're talking about the massive, complex routing of software data events that literally keeps a smart city functioning. We'll be unpacking a fascinating new paper that proposes a groundbreaking way to monitor this exact system. We're going to zoom all the way in, taking a journey from the scale of sprawling megacities right down to the microscopic routing of a single software data event.
So, here is our roadmap for today. We'll kick things off with the smart city ecosystem, followed by the role of smart contracts. From there, we'll examine the current monitoring gap and a proposed new monitoring system. Finally, we'll break down how the architecture works and finish up with the future of integration.
Section 1. The Smart City Ecosystem, Preparing for 2050. Let's start with the macro context so we can really grasp what's at stake here. To understand why this invisible infrastructure is so absolutely crucial, just think about this number. According to recent research cited in the paper, by the year 2050, over 2/3 of the entire global population will be living in urban areas. 2/3. This massive urban migration is giving rise to megacities. We're talking sprawling urban centers with over 10 million inhabitants. And to manage that level of explosive population growth, cities are pouring investments into information and communication technology to deliver digital services. This, in turn, creates a colossal, incredibly diverse software ecosystem operating across both public and private sectors. Now, for all these digital services to actually be useful to anyone, they have to talk to each other, right? Enter integration processes. Think of these as the literal nervous system of the smart city. They are specialized pieces of software that combine data and functionality from completely different systems. For instance, imagine a shop that automatically pays your parking ticket if you spend a certain amount inside, or a city municipality that automatically books a taxi for an elderly resident heading to a medical exam at the local hospital. These seamless, invisible experiences, they're only possible because of integration processes constantly humming away in the background. Moving to Section 2, the role of smart contracts and how they set the roles. So, if integration processes are the nervous system, something has to govern how they fire. You can't just have digital services blasting unlimited requests to each other all day long. The entire city's infrastructure would just crash. So there are strict restrictions governing these interactions. We're talking hard limits on the maximum number of requests allowed per unit of time, the maximum permissible response times, and the total amount of data transmitted per request. To enforce these rules without humans having to sit there manually checking everything, cities use smart contracts. These are self-executing software programs, often written in cross-domain languages like Solidity or general-purpose languages like Go. They contain programmable logic acting as an immutable agreement between digital services, usually executed on a blockchain. Which brings us to a crucial point. How do we actually track these rules? The paper really highlights two different approaches here: enforcement versus monitoring. Enforcement evaluates every single data event the millisecond it happens. If a rule is broken, it blocks the operation right then and there. Boom, stopped. But as you can imagine, this introduces massive processing overhead and latency because everything has to wait around for clearance. Monitoring, on the other hand, is independent and asynchronous. It checks for breaches after the fact, allowing the integration process to execute with absolutely zero latency. If a breach does happen, a compensatory action is triggered later. The paper champions this monitoring approach specifically because it aligns perfectly with the fast, event-driven workflows that a modern smart city demands. Section 3, the current monitoring gap. Why today's tools just fall short. Now, you might be thinking, well, if monitoring is the obvious answer, why aren't we already doing this? Well, the truth is the current tech landscape just isn't built for this specific need. Open source solutions out there like Grafana or Elastic require incredibly complex configurations. You literally have to cobble together tools like Promtail and Loki and build custom dashboards just to get it off the ground. Then you have cloud solutions like Datadog or Dynatrace. Sure, they're easier to set up, but they come with massive pay-as-you-go costs. But the biggest issue? Almost all of these tools focus heavily on tracking hardware resources, like memory and disk usage, or just the internal tasks of a process. They completely lack the ability to observe communication ports and invoke smart contracts using that event data. And honestly, that is a massive blind spot. Which brings us to Section 4, a new monitoring system, the missing puzzle piece. To bridge this glaring gap, the researchers are proposing a brand new architecture. Think of this proposed monitoring system as the immune system for the smart city. It sits right in the middle, bridging the integration platforms up top, where all the digital services are interacting, and the blockchain platforms on the other side, like Ethereum or Hyperledger Fabric, where the smart contracts actually live. It's an entirely event-based system, accessed through specialized APIs. It grabs the events reported by communication ports and asynchronously checks them against those immutable rules living on the blockchain. Section 5. How the architecture works. The journey of an event. Okay, let's zoom way down to the micro level now and track exactly how a single piece of data flows through this new system. Think of this as the hero's journey of a data event. Step 1, the event hits the inbound events queue via an interface known as API 3. This event comes carrying a header for authentication and a body filled with contract IDs and arguments. Step 2, the event handler asynchronously pulls this queue and validates the payload against the system's configurations. If everything checks out, it pushes the event along to the contract invoker. This third component is where the heavy lifting happens. It synchronously talks directly to the blockchain to execute that smart contract. Finally, the event updater swoops in, takes the results of that execution, updates the database, and pushes the final status out through API 5 so that any external applications can query it. But hey, things don't always go perfectly, right? This architecture actually anticipates that and clearly separates what happens when things go wrong into two distinct buckets. First, you have structure integrity exceptions. This is basically when the data is just poorly formatted. Maybe a contract ID isn't found or a required argument is missing. The event handler catches these right away, early in the process. The second bucket is the execution category. This happens later down the line and is handled by the contract invoker. This covers things like connection issues with the blockchain itself, or more critically, when a smart contract clause is actually violated by the data event. By separating these out, the system makes sure it doesn't waste precious computing resources executing badly formatted data on the blockchain. Finally, Section 6, the future of integration and our next steps. Let's zoom back out for a moment and look at how this actually gets implemented in the wild, because there are definitely some hurdles ahead. One massive practical challenge is figuring out how to get older legacy integration platforms to talk to the shiny new monitor without having to rewrite all their source code. The researchers are actually exploring a pretty brilliant solution using something called the decorator design pattern. Basically, this allows them to dynamically add behavior to software applications, essentially wrapping a new layer around it that talks to the monitoring system, without having to modify the original legacy code at all. Plus, security here is absolutely paramount. When you're connecting to cloud-based blockchains, you need access keys, and storing those locally is just way too risky. So the team is actively looking into integrating services like Bitwarden or Azure Key Vault to securely manage those crucial connection keys. And that leads us to the future of this technology, which leaves us with a truly exciting, almost mind-bending question. Right now, this system is inherently reactive. It monitors and flags violations after the data flows. But the paper points toward an incredible next step: integrating artificial intelligence. Think about it. Could AI soon analyze the flow of data across a smart city and actually predict parameter misconfigurations or smart contract violations before the integration process even has a chance to execute them? Evolving this from a reactive monitoring system into a proactive, predictive, self-healing urban nervous system, it's an absolutely fascinating thought to leave you with, and it just goes to show how incredibly dynamic the invisible infrastructure of our future cities is going to be.